So in this chapter, we will look at vector control of induction machines, but on a qualitative basis. So it's kind of nice to have a sort of a physical basis on which these machines are controlled before we make it quantitative that we have to in order to model them, in order to implement this vector control. But that we'll see in chapter 5. So let's begin. So let's say that we want to make the torque jump as a step. So imagine that your machine is running at a constant speed, but suddenly you want this electromagnetic torque produced by this machine to take a jump, as you see here at time 0. Okay, and in this case, it's a brush type DC machine. So what happens in a brush type DC machine? We have this field flux, which is produced by these permanent magnets, north and south magnets, which are shown here. And due to the armature and brushes and commutators, we have this armature flux phi sub A, which is at 90 degrees. So that's the purpose of these brushes and commutators, to keep this angle at 90 degrees. So what's happening is that in order to produce this step jump in torque, we cause this armature current to take a step jump at this time, and the electromagnetic torque is dictated by this equation here, which also takes a step jump. Okay, now let's look at this so-called brushless DC motor. Okay, so in brushless DC motors, which have been covered in the previous course, what we have, we have three-phase windings, ABC on the stator, and then we have a rotor with magnets. So north and south pole here is, we're just looking at two poles here, and the flux density distribution that is produced by the rotor and reaching the stator, that's the main thing, reaching the stator, is given by this space vector here, BR space vector. So as the rotor rotates and this theta mm changes, so does this BR, which is representing the stator, rotor-produced flux density distribution, would rotate. And what we have to do is to keep the stator current space vector IS at 90 degrees by properly supplying A, B, and C phase currents here. So here again, if you want to change the electromagnetic torque as a step, as shown over here, then what we need to do is to change this IS hat, which is the peak value of this IS space vector, so that we get the appropriate torque, making sure that as the rotor is rotating, this IS space vector is at 90 degrees. So that's really the kind of foundational stuff. What we really need to do is to look at vector control of induction machines. So if you go back to our previous course, what we saw that in steady state, we are applying some voltage space vector here. Let's say this is at time 0, and this distribution as time goes on, relative distribution wouldn't change of these space vectors. It just would rotate, okay, at synchronous speed. So we are applying this voltage space vector, and if you neglect the rotor stator resistance and stator leakage inductance, then the flux density distribution, I should say, produced by this stator voltages is given by this BMS space vector, which is at 90 degrees to this voltage space vector. And so in steady state, if this machine is providing some torque, there are currents in the rotor bars, and there's leakage in the rotor circuit. So the rotor MMF is given by this space vector FR. And so initially, when you didn't have any torque, there was some current I sub m over here. Let's call it IMS space vector. But because of this rotor MMF has to be nullified by additional currents drawn from the stator, which are represented here by IR prime space vector, and this rotor MMF FR prime is nullifying FR. Okay, so additional currents are drawn, and it's really the sum of this IMS, and again I should draw it with a lowercase I here, and IR prime, that is the stirrer current space vector. But because of the currents in the rotor bars, there's some leakage inductance, uh, leakage flux, which is represented by this. And so if you explicitly take the effect of that leakage, then what remains is this BR space vector. And you see that this current IR prime and BR at 90 degrees to each other. Okay, so that is kind of a genesis of vector control, that these two vectors are at 90 degrees. So in vector control, what we will do is we will keep the amplitude of this rotor flux density distribution, peak of that, BR hat, constant, but we will change this IR prime in magnitude, keeping this angle 90 degrees, such that we get this electromagnetic torque here, which we can change as a step. So that is the goal. So what I claim is that in vector-controlled induction machine, we have this steady state situation. How we got here doesn't really matter, but let's say we have this condition here where all these vectors are there, they're all rotating at synchronous speed, but if this machine is vector controlled and you want to go to a new value of torque, well, what you have to do is go to a new steady state, ideally instantaneously. It's not exactly going to happen because of certain reasons we'll talk about, but ideally we want to go to a steady state just like this, what you see here, instantaneously. So in understanding the physics of this, it's very useful to make an analogy with a current excited transformer. Okay, so there is a difference here between what we saw in the previous course. It's a current excited transformer with a short-circuited secondary here. So you can see the secondary winding is short-circuited through this internal resistance is shown explicitly, and to the primary we apply a step of current I1. Well, it's really not possible. So initially, let's talk initially. Initially, let's say that this, of course, we have the structure, the secondary winding is short-circuited, but we have no current in the primary. Well, if that's the case, there can't be any flux in this magnetic core, and therefore the flux linkage of the secondary winding at time t 0 minus. So this is at t equal to 0 minus, it's 0. Okay. So now we apply a step current here to the primary. Well, that's kind of problematic because there's a leakage fluxes over here, due to the primary winding current. But let's say that we ignore them, or even, but they cannot be. I mean, they will be there. There's no question. And but they apply certain volt seconds. So this I1 may not go as a step, but may go as with some certain slope. That certainly is possible, right? But for now, that's really not our concern at the moment. So let's assume that the primary winding leakage is 0, and we can make this current I1 jump, as we have seen here. So if we can do that, then the second, but coming to the secondary, that is really our main concern. It's a short-circuited secondary. Okay, so the theorem of constant flux linkage says that at t equal to 0 plus, the flux linkage of this coil, short-circuited coil, cannot change. So that has to remain 0. Okay, as you can see from here. So what's happening is that when you apply this current I1, there's flux in the magnetic core due to I1, and then instantaneously there's current I2 that will flow. Okay, and due to this I2, there are two types of fluxes, and one is this, which is a magnetic flux in the core, phi sub m I2, and then there's a leakage flux here. Okay, so you see that the sum of all these fluxes, the net, should be 0 in order to keep this flux linkage at t equal to 0 plus to remain 0. Okay, so you can say that if you take this in the positive direction, these two are in the negative direction with the negative sign, then the sum of all these three is equal to 0, and we can rewrite it in this fashion over here. So, if you see here that these are all linking n number of turns, and in this case we chose the number of turns to be the same, but of course they don't need to be the same. And I purposely cut this air gap to resemble it more to a machine where you have a rotor and stator separated by an air gap, right? So that's why I cut this here. And also, in the rotor we assume the same number of turns as the stator. So n equal to n is not a bad idea here on both rotor and stator side. So you can see that this lambda 2 is made up of this flux, uh, uh, phi sub m I2, and this phi leakage flux. And if you think that they are negative, then the minus sign shows up here, and then due to the flux from I1 here. So from here you can see that these two quantities together make up L2 I2, because L2 is equal to L sub m plus L leakage 2 here, right? so you can see that we have this expression for lambda 2. And I'm not sure it's worth belaboring this point, but we can see a little further what's going on here, that we have lambda 2 as we described earlier, this equation here. And so make sure that I'm writing it correctly. So this is due to I1, so that's where this I1 shows up, and these two are due to I2, so I2 is over here. Okay, so I have written this equation here, and at time t0 plus, this flux linkage is 0, so these two terms equal, summation equals 0, and therefore I2 at t equal to 0 plus is related to this step jump on I1 by this Lm over L2. And this will be exactly equal to 1 if the leakage was 0. But we want to take leakage into account. So you can see that once this current I1 begins to flow, this term here is 0, and we have two other terms due to the magnetic flux produced by I2 and the leakage flux. So you can draw this circuit, and the thing to see is that in this case, this I2 would decay if you don't do anything, because of this resistance R2 over here of the secondary winding. So as you can see, when you have this jump in I1, I2 jumps to this value, and this will decay out with some RL time constant. And we'll see in vector control, we do not want that to happen. Okay, so here also, if you can insert a battery which opposes the drop across this resistance, we can avoid or prevent this I2 from decaying out. So essentially, we are adding a battery, so to speak, to prevent that from happening. And how that happens, we'll see. Okay, so you can also see it with a transformer equivalent circuit analogy, but really a circuit type analogy, that when you make the change in this current I1 over here, this current splits into two parts, I2 and IM, and initially this leakage is much smaller than this, so I2 reaches this value here, but slowly this I2 decays out, and eventually this IM would become equal to I1, and this I2 would go to 0. Okay, so that's what will happen in this circuit here. Okay, so let's go on to the machine. That is our main concern. So we have seen this DQ axis representation in the past. Okay, so we have three-phase windings A, B, and C. We can represent by D and Q axis windings, one on the stator, one on the rotor, and these two are coupled, and these two are coupled, and there's no coupling between these two. So a set of 6 mutually coupled windings, we have reduced that to two sets, each one having two mutually coupled windings here. All right. So in vector control, let's say that we start by first establishing the flux in the machine. So how do we do that? Initially, everything was zero, nothing, no currents, no fluxes, okay? But slowly we build currents in phases A, B, and C such that along the A-axis, which is also, let's call it D-axis over here, this flux density distribution peaks. So let's say that we are building up these currents slowly, and so these currents, as shown by these expressions, you can see that in phase A we are, supplying this rated current, and phases B and C have the rated current in opposite direction, and that will produce this ISD to be this value, which will be related to the rated value like this here, and let's say this ISQ is 0. Okay. But please remember that everything is happening in ABC frame, right? But here we are representing them with the D and Q axis winding. So ISD reaches this value, and ISQ is 0. So this is the situation at t equal to 0 minus. There is no torque, and therefore rotor is not going anywhere. It's stationary. Okay. So now we want to make a step change in torque experienced by the rotor, okay, at t equal to 0 plus. But we still want to simplify our analysis. Somehow we block the rotor. Rotor is blocked from turning. So omega mechanical or omega m electrical is 0. Okay, so it's not going anywhere, and so we keep this current ISD applied to D-axis winding. So I should really plot D-axis over here. Okay, and so suddenly at time t equal to 0, we from 0 to a certain value, we apply ISQ here. And again, we are assuming that you can apply ISQ as a step without worrying about the leakage of the stator winding. Okay. So initially in the Q axis, this flux linkage was 0, right? So if that was true at t equal to 0 minus, it should be true at t equal to 0 plus. So as soon as we apply this current ISQ, there's a flux that crosses the air gap and links the rotor in the D-axis. But so immediately currents are induced in these rotor bars, and these currents produce a flux which again is magnetizing, so M subscript over here, because these flux lines cross the air gap and go to the stator. Okay, but then there's another component which is the rotor flux, which doesn't go to the air gap. Okay, so that is shown by this phi sub LR. The bottom line is that the net of all these three flux lines, one due to the stator, one due to the current, which is rotor bar currents, but flux distribution is reaching the stator. The third one is leakage. All three combined is equal to 0. Okay. And we also see that then you may ask why this sinusoidal current density distribution in these bars. Well, you can see that if you take a sort of a coil made up of X and X prime, it's cutting more flux lines. So it needs more current. And similarly, if you take a coil made up of Y and Y prime over here, and it's cutting less, it has less flux lines, so it needs less current. So automatically, the current distribution in these rotor bars, you can say, is sinusoidal. Okay. So now we want to maintain this distribution that we saw. So here also, coming back to this, you can see why a torque is produced, because we remember that force is equal to BIL, right? Or BLI or whatever. BIL thing, Bill. Okay, BIL. So you have these bars which are being cut by this flux density distribution produced by the D-axis like this here, and then you have these currents over here. So on each bar you have a force produced and you have a torque. So instantaneously you have this jump in torque, which was 0 here, and then it, well, if you take this as 0 line over here, it was 0 and it jumps. This electromagnetic torque is what I'm plotting here. So that is happening at time 0 plus. Okay, but now if you want to maintain this torque, again assuming that the rotor is blocked from turning, and which restriction we'll remove very soon, and I'm just again showing it at 0 plus here to make certain points here. As you can see that these fluxes show up like this in order to have the net flux linkage in the Q axis of the rotor to be 0, and since we are not changing ISD in the D axis, this is constant here. So same as it was at T minus, 0 minus. Okay. So here it's showing that what the three flux density distribution space vectors are doing. You had this here because of you have leakage flux, the net flux is over here. But the bottom line is that the torque that is produced is proportional to the peak of this flux density distribution and times the current ISQ, but there's a factor here, Lm or Lr, because of leakage. Because if there was no leakage, then Lm would be equal to Lr, right? If no leakage, if L sub leakage is 0. Okay, so it's sort of qualitatively showing that this is the expression we get, and this how we compute K1 that we'll deal with when we make it quantitative in chapter 5. So now we want to maintain that distribution because we want to keep this electromagnetic torque constant, right? It was 0 and then it jumped like this, right this here. And we want this to be constant, let's say. And rotor is still blocked from turning. So rotor is still blocked, okay? So in this case, what we have to do is to rotate this D axis and Q axis at appropriate slip speed so that this flux density distribution that is being produced by ISD, this flux density distribution is cutting the rotor bars, because rotor bars are stationary. Remember that rotor bars are stationary, but the distribution changes, and you can see that the maximum current that you have is where this flux density space vector is peaking, just like in this diagram here. Okay. All right. So I'm sorry, I'm going the wrong way here. So now we would like to calculate what this slip speed has to be. Well, what we have to do is to cancel the voltage drop across the resistance of these bars by voltages induced due to the rotation of this B sub R flux density distribution. Okay, and so you can see that you can read all this here, but the bottom line is that this slip speed, and we'll derive a very concrete expression for this, is proportional to this ISQ, which is indicative of how much torque you wish to produce, and this factor shows up because of leakage, and then depending upon how much resistance you have in these rotor bars, which is represented by this equivalent way is R sub R prime. So it's proportional to these here, but also it's inversely proportional to the flux density distribution peak, which we'll be keeping constant. So all these things all get put in place. So what we have to do is to maintain this distribution, the relative distribution, the same as time is progressing. We saw that when the rotor was blocked. But why does the rotor have to be blocked? The rotor may be turning and maybe providing certain torque, and this torque doesn't have to be 0. Maybe initially it was over here. Okay, there's 0, and you want to change this as a step, right? So it was initially turning at some synchronous speed, and at some slip speed, and when you make this torque take a jump, well, instantaneously the slip speed has to increase, and therefore the synchronous speed has to increase. So, what we saw under the conditions of a blocked rotor, it can easily be seen when the rotor is actually turning. And that's really the bottom line, because we will be making this a torque jump, if that is necessary, uh, under vector control. It will be under a condition when the rotor is actually turning at certain speed. So the main thing is that we want to keep this relative distribution the same as the rotor is turning, but these currents may be of different values to produce different electromagnetic torque. So that is, kind of shown in this block diagram here for the control, but I think it doesn't really give much of the physical intuition at this stage. We'll see that anyway in chapter 5. So I think we should just you know accept that all this is done under a closed loop condition, this vector control, and there's a torque loop, there's a outer speed loop, and then there's yet another outer position loop. Okay, so all these things will come together, and we'll see that in chapter 5. Thank you.